Okay, 8-2 Pythagorean theorem, and one that you've heard before, and you'll hear it many, many times again. A Greek mathematician named Pythagoras came up with this Pythagorean theorem 2,500 years ago. And there's been different proofs of that theorem, but let's just state what the theorem is, and that is that the square of the hypotenuse of a right triangle is equal to the sum of the squares of each leg. So in the case where we have one side here, AC, if that is equal to little b, and this BC is here is little a, and the hypotenuse is C, then we have C squared equals A squared plus B squared. So the main proof of this comes from, first of all, drawing a perpendicular from the point C down to the hypotenuse of the right triangle. And we could do that because if we take a point to outside a line, there's exactly one line that is closest to that, and that is the one that is perpendicular. And so perpendicular. Now we set up these ratios. C over A equals A over E. C over A equals A over E. And also C over B equals B over D. So that comes from the previous section where when we drew an altitude to the hypotenuse of a right triangle, then each leg is the geometric mean between the hypotenuse and one of its segments. All right, so a property of proportions is that we can multiply the means times multiply the top of the left times the bottom of the right. Those are the means and the extremes. So they're equal to each other. C equals A times A. CD equals B times B. And so now we have, because of that property, we can write this out. We can add CE plus CD, and that will be A squared plus B squared. And that's just the addition property of equality. Then if we factor out the C from CE plus CD using the distributive property, then we can replace E plus D with the C, and that makes this C times C, or C squared, and we have the Pythagorean theorem proof. So the types of problems that you have with these are ones where either the leg, we're trying to find the length of a leg, or we're trying to find the length of the hypotenuse. So in problem A, this is in the formula would be like A, B, and C. So we would say that A squared plus B squared equals C squared, or 3 squared plus 7 squared equals X squared. So then we do 7 squared plus 3 squared, and that's 58. And then the square root of that is square root, or radical 58. And there's no perfect square that comes out of that, so we're done with that problem. Now let's say we had a problem where we already knew the hypotenuse, but we didn't know the legs, or that we knew that they were related to each other. Then we could just do the A squared plus, or this one would be, this is the B and this is the A. A squared plus B squared equals C squared. We have to multiply that out by FOIL. And we end up combining x squared and x squared to get 2x squared plus 4x. Subtract the 100 to get 96. We can factor out a 2 GCF, and then the bottom, the last line is factoring out that quadratic to get x plus 8, x minus 6. And so that means either x equals -8 or x equals 6. We throw away the x equal -8 because this is a side length, and length has to always be positive. So our answer is going to be 6. Okay, so the rest of these problems are just a matter of working out the different possibilities with the Pythagorean theorem. Problems 5 through 9 are just going to be simplifying expressions. One of these things here is if you take the square root of some number and square that, you will get back to the number that's under the radical. And we know that because square root 5 times square root 5 is square root 25, and square root 25 equals 5. So whenever you see some quantity squared, it's going to be back to that original number. But what if you have something inside that's not part of that radical? Well, then that has to be squared separately. So this one would be 2/3 squared times square root 6 squared. All right, so take a look at those, and then also the written exercises, and then we'll move on to the next section.